I study how things mix in fluid flows. It turns out that some very simple flows can give rise to very complicated mixing. The background, my area in general is called nonlinear dynamics, or the flashy name is chaos, or chaos theory. And the basic idea behind chaos is that some very simple systems can behave in tremendously complicated ways. So this is just two pendulums hinged together, and yet the behavior is extremely complicated. And actually, let me give it a nice big push here. It turns out that you can write down the differential equations for this system here, but you can't solve them. In fact, it is mathematically impossible to solve it. This is something that your math classes may not have told you about. Most differential equations have no solutions. It turns out that when that happens, you often get very complicated behavior in what should otherwise be a very simple system. So in my case, I'm studying chaos, but chaos in fluid mixing. Imagine you've got a big pot of soup, and you have some pepper, you shake the pepper in, and you want to mix the pepper in. What do? Well, if you have a nice clear fluid, like a chicken broth or something like that, you take a spoon and you stir the living daylights out of it. When you stir the living daylights out of it, the fluid is mixing, the fluid flow is turbulent, and you get good mixing. But what if it's a pot of cream of mushroom soup, which is really thick? You can't stir it turbulently, so instead, if you stir it in a circle, that's very bad for mixing. But if you stir one side and then the other side and alternate back and forth between the two of them, it's about a factor of 100 better mixing. And the reason for that is that the pepper flakes will actually undergo a chaotic path in the soup. And so if you have a bunch of pepper flakes, since they're all undergoing chaotic paths, they separate quite efficiently. Half of the research that I'm doing is basically understanding how different fluid flows give rise to different kinds of mixing. But basically, if you can get the behavior to be chaotic, you get much more efficient mixing. Big drum of gasoline, pour it all over the floor, light a match, drop the match. Of course, where the match hits, the gasoline is going to catch on fire. But what's going to happen is a flame is going to move across the floor. And as it moves across the floor, in front of the flame you've got the gasoline, behind the flame you've got the exhaust, and the flame itself is a reaction front. So the question is, how does that front move across the floor? If you don't stir the gas, that's pretty well understood. But what we're doing is we're saying, well, what if we're stirring that gasoline as that flame front is moving? So this would be analogous to looking at reaction fronts moving in the ocean or in the Gulf of Mexico, or in the case of a disease propagating through a society where the people are moving around. That's kind of the basic picture of what it is that we're looking at. There's some fluid and it has some fluorescent dye, and what's happening here is that laser beam is basically forming a sheet, and when it's every 10 seconds it'll take a stack of images here, and you'll actually see the beam moving upward. So you see how it's kind of scanning through there? And so each level, while it's slicing through, it's showing you the dye at that particular level. And of course, whether you can actually see that. Mm-hmm. And so from that, basically we have a camera over top of this. And so if you imagine kind of slowing this down, you get the beam scanning at one particular height. The dye that fluoresces at that height shows up in the camera, and then it moves to a different height. And so you can actually assemble all those images back together and get a full three-dimensional image. It'll go very fast. Can you see all that? Yeah. So basically what you're seeing there is a grouping of 32 images. Each image is at a different height, and again, like the magnetic resonance device imaging, you can kind of reconstruct that to get the full picture of what the dye is doing in 3 dimensions. So the word discovery, I think, is very appropriate in this case, because we're not inventing these laws. I would love to be able to say that I came up with all this, but I didn't. The universe was already here, the laws were already here, and we are discovering what those laws actually are. Discovering how the universe actually works. And of course, the cool thing about this is the more you learn about the universe, the more you realize just how amazingly cool it is. So yes, this is where discovery happens, but this is only one of the places where discovery happens. And maybe I just gave you your tagline right there.